Welcome to This Explainer. If you've ever wondered how a rough, totally basic piece of bar stock miraculously transforms into a gleaming, high-precision component, well, you're in exactly the right place. Today, we're diving deep into the world of CNC turning. We're going to unpack the complex physics happening inside the machine and translate them into highly practical, floor-ready strategies. Whether you're a rookie operator, an engineer, or even a purchasing manager, mastering these basics is absolutely crucial for unlocking real manufacturing efficiency.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the core basics of CNC turning, then tackle facing and how to eliminate those annoying center pips. From there, we'll look at straight turning and part deflection, followed by advanced internal operations like boring and threading. Finally, we'll wrap up with the data comparison matrix and some material-specific cutting advice. Starting off with Section 1. Let's establish the fundamental mechanics of the lathe before we make our very first cut.
Now, turning isn't just about spinning metal around. Fundamentally, it's all about relative motion. The workpiece is locked firmly in a chuck or collet, and that provides the primary rotation. Meanwhile, the cutting tool itself doesn't spin. Instead, it glides along the X and Z axes to provide the feed motion. So it's really this precise interaction between the tool's rake angle and the material's shear strength that dictates how a metal chip actually forms and peels away.
So the absolutely crucial point here is balance. If you want high-volume, precision production, balancing your material removal rate, or MRR, is non-negotiable. You can't just crank up the speed. You have to find that perfect sweet spot between ripping material away, preserving your tool life, and maintaining the surface integrity of the part. And you do that by expertly managing heat, usually with proper coolant application, and picking the exact right carbide grade for your cutting insert.
Moving on to Section 2, let's look at the very first operation in our cutting sequence, facing. This is where we establish our Z-axis 0 and strip away that rough, oxidized outer layer. Now, if you're a beginner, you've definitely run into this frustrating issue. You make a facing cut and why is there a tiny bump right in the middle of the part? And more importantly, how do you fix it? This is the dreaded center pip. It's a stubborn little nub of metal left right at the rotational center, and if you don't get rid of it, it will literally ruin your downstream operations, especially drilling.
And this brilliantly illustrates how precision works on a lathe. That pip happens because the tool height isn't perfectly matched to the spindle's true center line. To permanently solve this defect, you have to align your tooltip height with that center line down to the micron, literally within microns. Once you're perfectly locked in, the tool sweeps flawlessly across the face, eliminating the pip and giving you a perfectly flat datum for everything that follows.
Let's head to Section 3. Moving chronologically down our bar stock, we get into longitudinal straight turning. This is how we take the outside diameter down to a specific, highly accurate size.
In practice, this happens in two distinct phases, using speed and feed to achieve totally different goals. First, the roughing cycle. Here, you're going for maximum MRR, deep cuts, high feed rates. You're just hogging out the bulk of the metal, leaving a tiny bit behind. Then you switch to the finishing cycle. Now you take a very shallow depth of cut with a low feed rate to gently shave off that last layer and achieve your final raw tolerance and a pristine surface finish. But here is a massive troubleshooting question. How do you manage part deflection when you're turning long, slender shafts? Because of the sheer physical force involved, the tool literally pushes the workpiece away from it. On a skinny part, this creates a tapered effect, meaning the middle ends up physically thicker than the ends. Not good.
The fix? When you are turning slender shafts, you absolutely must utilize tailstocks or steady rests. These external supports brace the workpiece against the thrust of the cutting tool, ensuring your final cylinder remains perfectly uniform from end to end without any taper at all.
Okay, Section 4. Let's shift our focus from shaping the outside to cutting complex internal geometries, which require some seriously delicate synchronization.
Internal machining is kind of a two-step dance. Step 1, drill a starting hole to get rid of the bulk material. But here's the thing, drilling alone isn't enough because drills have a tendency to walk slightly off-center. So step 2 is mandatory for high precision. You follow up with a single-point boring bar. This doesn't just enlarge the hole, it actually corrects the concentricity, ensuring perfect alignment with your external diameter. Now, I want you to remember this specific number, 4. This represents a hard physical limit known as your length to diameter, or LD ratio. If your boring depth exceeds 4 times the hole's diameter, standard tooling is going to vibrate and chatter like crazy.
If you want a smooth finish past that ratio, you have to switch to specialized carbide-reinforced or dampened boring bars. No way around it. Now, what's really interesting about this slide is threading. This is probably the most complex operation on the lathe. You aren't just jamming a tap in there. The CNC uses complex single-point logic, like G76 or G32 cycles, to move the tool longitudinally in perfect, exact synchronization with the spindle's rapid rotation. It tracks a helical path flawlessly, entering the exact same groove over multiple passes to cut custom pitches and multiple start threads.
Section 5. We've covered a lot of ground, so let's pull it all together into a master cheat sheet that maps operations to their toolpaths and standard tolerances.
Let's move through this matrix and see how it builds. Radial paths for facing create flat references, usually accurate to within 0.01 to 0.05 millimeters. Longitudinal straight turning drops the OD with incredibly tight tolerances, down to just 5 microns. Taper turning combines X and Z moves for conical shapes, while boring handles internal longitudinal corrections. Finally, parting moves radially to the center to sever the finished part from the stock. The direction of your path directly dictates your precision limits.
All right, Section 6. Let's introduce the final and, honestly, most critical variable in our machining journey: adapting your settings based on the raw metal itself.
You simply cannot cut every metal the same way. For aluminum, you need extremely high speeds, usually over 3,000 RPM, and highly polished rake surfaces, or else the metal basically welds itself to the tool, causing built-up edge. Stainless steel, the big risk there is work hardening. You have to maintain a constant, aggressive feed rate and use robust cooling. If the tool rubs instead of cuts, the surface hardens instantly and ruins your insert. And titanium, well, its low thermal conductivity means the heat doesn't leave with the chip. It builds up right at the cutting edge, so you have to prioritize heat dissipation and significantly slow your speeds down to survive the cut.
So what does this all mean in the real world? If you're an engineer or a B2B buyer, ask yourself, how does a deeper understanding of these parameters optimize your total cost of ownership and supplier selection? When you understand why a center pit forms, or how deflection ruins slender parts, or why titanium needs specific feeds, you aren't just looking at a price tag anymore. You can actually evaluate a supplier's true technical capability. Mastering these core basics directly impacts your bottom line, slashes cycle times, and ensures you actually get the precision you're paying for. I hope this beginner's guide leaves you totally fired up to explore more advanced CNC programming. Thanks for joining us on this explainer.